Alright, so we're going to talk now about gravity and the equation used to calculate the gravity of or gravity that exists between two objects. And this is mostly Newton's ideas and the universal law of gravity. Now a little bit, maybe tomorrow or the next day, we're going to talk about Albert Einstein's contribution to this and special relativity. And it kind of adds to the idea of Newton's understanding of gravity. So I want to open this real quick. Just give me a second here. Close that. Oh, there. Okay. So, when we look at gravity, usually we start with Newton's universal law of gravity. So universal means it fits all things. Okay. And Newton looked at gravity as a force that all objects possess. And really Einstein would agree. His law of special relativity, really it exists between all objects. And also Newton understood that because it's a force, that it then relates to interactions between objects and any object. So whether you're a person, draw a stick figure, you could be alive, you could be a bowling ball. It's kind of a big bowling ball. So we could be a car. Okay. And or you could be a little bug flying in the air. Okay. They all have gravity, and you'll see why when we look at his equation, which is just right here, why he thought that. Because when you look at this equation, you have this g, and we'll talk about that. That's a special constant for gravity. But then it also includes the m is mass of one object to the mass of another, and then the distance between those masses squared. And this equation we'll look at in a minute. But he came to understand that that gravity, or the force that one object enacts on another or applies to another, depends on the mass of the objects and the distance they're apart. So, and this really gets into the radius. So if you have like the sun, and then you have a small planet out here, and the distance is really the distance between these two objects. And really it's a radius because these things are going around in a circle, right? So it's really a radius. And this generally stays the same. Planets don't orbit in perfect circles, but they're more elliptical, which is like an oval or an oblong circle. But it's that idea that the distance between any object to determine gravity is how far apart they are. And then we even consider the radius of the object itself. Now sometimes that won't matter, because if you're talking about 90, let's say this is the Earth, 93 million miles, and then a really big number, and then if this radius is equal to 10,000, when you relate it to 93 million doesn't really mean that much. And the sun even, I'm not sure what its radius is, but in the grand scheme of things, does it really add much to 93 million? You just have to see if it does or not. Now in the end also, if you included the radiuses of each of these, it wouldn't affect the calculation at all. Okay, so just remember that mass and distance, that is really what determines the amount of gravity one object exerts on another. Now we have the equation here, so I'm going to clean this up. So we have the equation for gravity, and let me move this down a little bit. So this is f of g equals g times m1 times m2 divided by r squared. And really that's the distance between masses. So if I was going to write this out as just a simple equation, F of g, the force of gravity, equals g m1 m2 and then you divide it all by the radius, and you square it. Now, this square is pretty important, this little squaring thing right here, because as radius increases, the effect it has on gravity doesn't double, it quadruples. So, and it doesn't make it greater because it's on the bottom of this equation. If you know math, this is just going to divide into that. So if you think, just for example, let's just make these easy numbers. The mass is 1 of one object, the mass is 1 of another, and let's say the radius is 1. Okay, so then the force of gravity would be 1 times 1 is 1, and we just don't worry about this right now, just for this demo, but these are all 1 over 1, so the force of gravity is 1. Okay, so then let's say we move this twice as far, so then they spread out, and radius, the mass doesn't change, but then the radius becomes twice as far, and you would think, well, then gravity is going to be reduced by a half, right? But it's not, it's actually a fourth, because this is squared. So this stays 1, and then this then becomes not 1, but 1 over 4. Okay, and so it has this quadruple effect. So by changing this radius, you really affect gravity greatly. That's why you have the sun, you know, it's just a giant object in space, and then you have Mercury, Venus, you have Earth, I don't think these are right sizes, but Mars, and then we have, you know, the moon going around the Earth. And that's why, you know, when we're on the Earth, if we're a little speck down here, it's kind of big actually, but it, you know, if it were the right size, the gravity that we feel is not from the sun, although there is some. It's mainly from the Earth because we're so much closer. When you start getting this giant radius and you compare it to how close we are to the Earth, the greater force is from the Earth, and even maybe from the moon as well. Okay, but this is the equation we use. And you can see here, this is the constant, and you have to kind of remember this because it's a big one. And you might want to write it down in your books that you have, your equation books. But it's 6.673 times 10 to the negative 11th. Okay, and then you're going to see also that these masses of planets are ridiculous. They're just huge. So scientific notation is really something you might want to practice a little bit because you're probably going to need it. And if you try punching some of these numbers into your calculator, you don't do it the right way, you could get the wrong answer and not know why. Okay, so that's kind of the introduction to the equation there. Let's erase this. And then, but what's interesting about gravity is it results in tides, because this is, you know, the moon is the huge one, but also the sun somewhat causes, you know, as a pull on the water, but the moon definitely does, and we'll probably look at this in an article. But also gravity causes elliptical orbits. So if we were going to draw this out, and when we look at Kepler's law, we're going to it's not a very good one, but it's alright. And here's the Earth, and if this was a ellipse, it has two foci, and the pattern that a planet would take as it orbits around a sun, you'd have this sun right here, and then the planet's here, and it just follows this path. So the star is at one foci, and the planet is at another. Now I'm really exaggerating this. It's just barely an ellipse. It's not very much of an ellipse, but it is an ellipse. It's not a perfect circle. So all the planets go around the star in an ellipse. And when we look at Kepler, we'll look at that in much more detail, but keep that in mind. So these gravity causes orbits the planets have, and they're ellipses. And also with gravity, it helps determine our weight. So if you're thinking on the Earth, what's my weight? How much do I weigh? That's due to the force of gravity. Okay, and that is really, the W is just the F of G. Okay, and we just take the mass of the person, and then times gravity times 9.81, and then whatever your masses would be without gravity, you multiply it by the acceleration due to gravity, and that gives you the force. And that comes from Newton's second law. Force equals ma. So we can figure out the force of something if we know the mass and we know the acceleration, and the acceleration of gravity on the Earth is 9.81. And then we can just, if you want to know what your weight would be on Jupiter, Saturn, Mars, whatever, you could figure out what is acceleration due to gravity there, and then you could figure out what your weight would be. But that's kind of the introduction to gravity. And check them out, annotate them, and turn them in. And I'll talk to you later.